Hello students, Dr. Regmi here. In today's lecture video, we are covering a completely new concept about equilibrium from chapter 6. Okay, in order to understand that, let us look. Until now, we had been always talking about the irreversible reaction. Okay, it means we were talking about, let me choose a pen. We were talking about the reaction where the reactant will collide with each other and making the product, right? So this is called irreversible reaction because we have one way. Only the reactants are prone to make the product. Okay, but today we are going to learn about reversible reaction. Reversible reaction means we are talking about those special reaction where reactant can form the product, and now products are also prone to combine with other products and form the reactants back. Okay, so we have here reversible reaction. Reactants becoming product is a forward reaction, and products becoming reactant back is a reverse reaction. So in a reversible reaction, both forward and reverse reaction are possible. So in today's lecture video, we are going to explore this kind of reactions. We are going to understand what the equilibrium is, what are the different characters of the equilibrium, and we will learn about Le Chatelier's principle. Okay, so let's get started. Let me do the slideshow here. So let us suppose we have a reaction. Okay, I have here CO, carbon monoxide, okay, reacting, let me go back, carbon monoxide forming the, reacting with water to form carbon dioxide and hydrogen gas. Okay, when CO molecule and the water, they do combine, these are the two reactants, they do combine and form the product we call the forward reaction. Okay, the forward reaction will always proceed to the right. And now we have the products, carbon dioxide and hydrogen gas. Now they will also collide with each other, and now they can form the reactants back. We call this reverse reaction. It proceeds from the right to the left. And we have a reversible reaction. Okay, we represent the reversible reaction with the arrow that shows both direction, because both direction are possible. So our arrow looks like with double head. Or you might see in the book we will use two arrows, one arrow going to the right, other arrow to the left, to show that this is a reversible reaction. Okay, now when the rate of the forward reaction, okay, the way the products are forming is equal to the rate of reverse reaction, okay, the speed of forward reaction and the speed of reverse reaction, both of them are equal. Okay, so the rate at which the changes of the reactant to product and changes of product to reactant over time is equal, we have a special condition. We call this special condition equilibrium, right? In English, equilibrium means equal. When the forward rate and the reverse rate, right? Forward rate and the reverse rate, these are equal, we have equilibrium state. Equilibrium state is known as balanced state, right? We have very balanced state during that particular moment. Okay, the condition is the forward reaction should be equal to the rate of reverse reaction. We call this equilibrium. And during equilibrium, the net concentration of reactant and products, they do not change. What does it mean? We will explore in our next slide. Okay, so it means that the concentration of reactant will remain constant. There will be no change in it. Similarly, the concentration of product will remain constant. So when we have this concentration ratio, we take the ratio of them, the relationship will be a constant number. From there, we introduce a constant called equilibrium constant. Okay, so let us understand this with an example. Let's say I have a general reaction. I have A moles of A react with B moles of molecule B, forms C moles of product C and D moles of product D. Okay, the coefficient are here represented by the letters. The coefficient can be any number here. Okay, and we have here, this is a reversible reaction. It means that the reactants can combine to form the product. The products can collide with each other to form the reactants back. Okay, and now we have this double arrow, means we can tell that this equation is at equilibrium. Whenever we have an equilibrium reaction, we can write the expression for equilibrium reaction. Okay, so the expression of equilibrium reaction has the equilibrium constant. Okay, it is represented by uppercase K, will be equal to the concentration of products divided by the concentration of reactants in general. Okay, here we have product C and product D. Okay, and they will be, whenever we write the square bracket here, this square bracket means we are mentioning the concentration in moles per liter unit. Okay, for now, understand this is concentration. Okay, so we have the ratio of concentration of product divided by concentration of reactant. Okay, we also need to account the coefficient of the balanced equation. Okay, so the product should be raised to the power, okay, raised to the power, and those power directly come from the coefficient. Similarly, the reactants will also raise to the power of their coefficient. So for this particular reaction, the equilibrium constant can be written as, I have uppercase K, okay, equal to, since I have two products C and D, I will write the C and D in square bracket. Now C has the coefficient C, so I will write the lowercase c as a coefficient there, raised to the power C. D will raise to the power D. Okay, divide that by reactants. Always the reactants are on the left hand side of the arrow, right? So I have here A, one of the reactant, and raised to the power lowercase a, the coefficient of A, and then I have B raised to the power coefficient of B. Okay, so actually we have a multiplication sign between them. Okay, if it is not obvious to you, understand that there is a multiplication sign. So we have C and D products raised to their respective powers, divide by A and B reactant raised to their respective powers. Okay, so this is the expression that relates the equilibrium constant with our concentration of reactants and products. Okay, always remember, it is product on the numerator and it is reactant on the bottom. Sometimes the student just flip it and that they do make it wrong. Okay, so we have here products divided by reactants. The ratio is called equilibrium constant. The constant means the equilibrium, the value of K will remain unchanged even when we play around and change the concentration of either reactant or product. Okay, that's why the earlier slide told us the ratio of products to reactants, it will remain constant, means the equilibrium constant will remain unchanged. Okay, the value of equilibrium constant will be the same for that particular reaction, no matter the concentration of reactants or products are changed there. Okay, as long as you are doing the reaction at same temperature, the equilibrium constant will have a particular value associated with that reaction. Okay, so let us look one example with here. Let me, example here. We have N2 plus O2 forms NO, and we have an arrow showing here, double arrow. Okay, so the equilibrium constant, if we want to write it for this reaction, then equilibrium constant is K, right? Uppercase K is equal to, I have the product NO, nitrogen oxide, right? So I wrote there nitrogen oxide, the nitrogen oxide raised to the power 2 because my coefficient is 2 there. Right? Divide that. I have only one product, so I write just NO there. And now on the denominator, I have N2, so I have the concentration of nitrogen gas raised to the power 1 because I have one coefficient here. Similarly, right, it is times O2. The O2 oxygen also has coefficient 1. So we have here N2 raised to the power 1, O2 raised to the power 1. Power 1 means we do not write it to show it, we understand it. NO raised to the power 2, and then we have N2 and O2, right, raised to the power 1. So we have them here. So this ratio, the ratio of product raised to its power divided by reactants raised to their respective coefficient is equal to equilibrium constant. Okay, so please review, try some reaction, bring some reaction in front of you and try to write the equilibrium expression. This relationship, when you write K is equal to products by reactant, this expression, when you bring it, we call it equilibrium constant expression. Okay, and learn how to write them this way. Now, that value of K will give us some indication. Okay, it will tell us according to the magnitude of that K, we can talk what kind of reaction it is, or whether at equilibrium the reactants are favored or products are favored. Okay, so to that, let's understand K will have certain value. Let's give this a numerical value, let's say 1000. Okay, let's say the reaction that you are working with has the K value 1000. What does this magnitude 1000 mean to you? What is the significance of that number? Let's find out. When the K value is much greater than 1, okay, in our case it is 1000, so it is much greater than 1. What does it mean? It means that that ratio, right, K value was the ratio of product by reactant. It means that the products, the concentration of product is much larger than the concentration of reactant, right? It means the numerator is larger. It means the reaction is making a lot of product. We have a product favorable condition, right? And when do the products are favorable? If the reaction is forward going, right? So out of the forward and reverse reaction, if the forward reaction is dominating, then it favors the product, and it means when products have larger number, the value will be greater than 1. Okay, so whenever the K value is greater than 1, let me write his K value is much greater than 1. In that case, we understand the equilibrium is lying to the right. It is favoring to the right hand side of the equilibrium. It is favoring to form the product. Okay, that's what we understand. Now, if K value is much less than 1, Let's say you are doing an experiment, you calculated the K value of that experiment. It was, let's say, 0.00001. Okay, let's say it is very smaller than 1. K value is much, much smaller than 1. It means that now your product is small, the reactant is large. Because to get the value lower than 1, the denominator must be much larger than the numerator, right? So what do we understand? We understand that for this particular case, where K is much lesser than 1, for that reaction, we have reactants will be much more than the product, right? If you take out the equilibrium mixture, okay, the mixture at equilibrium, and inspect, right, whether you have the reactant molecule or product molecule more there, you will find there will be more reactant molecules. And actually we do have instrument to read those or find those, do those analysis. Okay, so for the case where the K value is much less, it means that reactants are more there. The reactants are more means this time when we compare the forward rate and the reverse rate, the reverse rate is dominating, right? The reaction is favoring towards the formation of reactant. So the arrow will look towards the left hand side. So we say the equilibrium will lie to the left. The equilibrium will favor to the left hand side, right? The arrow will look like this. It will favor the reactant. Okay. Now you might say, okay, I see the condition where K is larger than 1. I see the condition when K is smaller than 1. What will be the case when K is equal to 1, right? If you are thinking that, okay, when K is almost equal to 1, okay, it's around 1, it means that both the reactants and the products, their concentration or their number is equal. The numerator and the denominator, they are similar. When they are similar, the value is much closer to 1. Right? And that moment, that particular moment is the equilibrium. Okay. In this case, we say the reaction is perfectly at equilibrium. Okay. The K value will be equal to 1 means that particular reaction is at equilibrium position. Okay. So we are guessing, we are predicting the position of equilibrium by looking on the magnitude of K. We can do that, right? We just learn how to do it. So let's practice here, okay? As I mentioned, at equilibrium, both reactant and products are present in the similar amount. They are equal in amount. Then we have a perfect equilibrium situation. The equilibrium does not go left or right. It will be at balanced state, right? It will be right at balance there. The rate of the forward reaction will be equal to rate of reverse reaction. Okay, the concentration of product, the total products will be equal to the total concentration of reactants, so that the ratio will be 1. Okay, isn't that beautiful? Right? So we learn about the equilibrium constant magnitude and what information do we get. Let's try our concept and apply that. For a reaction, okay, we are given a reaction. Okay, here the double arrow, this is actually like this. Okay, this double arrow is in a different format here. The format is wrong. So we have a double arrow here. 2 hydrogen moles combine with 1 mole of oxygen gas to form 2 moles of water. During this reaction, when you calculate the equilibrium constant, you get this number, 2.9 10 to the power 82. Now the question is, who is favored, the reactants or product? Just by looking on the quantity, the magnitude of K, you should be able to say which one is favored. Okay, here the K is, you can pause the video, guess the answer and come back. Here the magnitude of K is 10 to the power 82. This one is a positive number. It means K is very, very, very greater than 1. Right? So whenever K is greater than 1, it means that your numerator, the products, is much more larger than your reactant. Right? It means that the products are the favored one. That's why they make large of them. And the equilibrium will lie towards the right hand side. Okay, the equilibrium will favor, I will write here, the equilibrium favors right hand side. That is what we got. And if the equilibrium favors right hand side, it is the product that is in the larger amount. Okay, so that is how we answer this question. If the question asks you, give me the equilibrium constant expression for this reaction. Okay, let me add that one more question here. If the question is something like that, then how do we answer? We write K, right, is equal to, I have to write product on the top. I need to write reactant on the bottom. I have two reactants on the bottom. And raised to the power. I have to remember that. Do not forget to raise with the power. I have here water, so I will write water. Water has the coefficient 2, so I need to raise the power by 2. The reactant hydrogen has the coefficient 2 in the equation, so I raise the power with 2. Oxygen, write all of the oxygen, okay? Write O2, do not write O only. You have to write the reactant as it is. O2 is the oxygen, the dimolecular oxygen molecule, O2. And then raised to the power simply 1. Okay, so it means we have water raised to the power 2 divided by hydrogen raised to the power 2 and oxygen only. Right? So this is equal to K. This is the equilibrium expression the question will be asking. Okay, I just added that question because I did not see that question here. I feel like you find it helpful to explore that. Okay, now with that information, yeah, which side does the equilibrium lie? I already answered that question. The equilibrium favors the right hand side, so equilibrium lie to the right. So this slide is a very good summary to sum up all the things that we just learned. If the value of K is greater than 1, it means equilibrium lies to the right. It favors the product, right? The position of equilibrium means it is to the right. If we have K value lesser than 1, it means at this moment the reactants are the favored one. It means the equilibrium favors the left hand side, right? The equilibrium lies towards the left hand side of the reaction. If the K is almost equal to 1 or equal to 1, okay, in that case, it means it is exactly at the equilibrium. The reactants and products both are present at the equilibrium. They have the equal amounts at that moment, okay? The concentration of reactant does not change. The concentration of product does not change. And then we have an equilibrium state there, okay? The ratio will equal to 1, the ratio of products to reactants. Okay, so this is the summary. Now, let's do one math question here. When we are given the equilibrium reactions, okay, and we are given the equilibrium concentration, then how to work for it. Data from the chemical analysis shows that at equilibrium, your concentration of SO2 is 0.44, O2 is 0.22, SO3 is 0.11. In that case, calculate the equilibrium constant. Okay, first of all, we need to know how to write the equilibrium constant for this expression. Okay, how to write the expression for this reaction. I bring uppercase K, right, capital K, and I know that it is the product that goes on the numerator. It is the reactant that goes on the denominator. Here I have two products, SO2 and O2. I will write SO2 raised to the power of its coefficient. O2 raised to the power of its coefficient. The coefficient is 1, so I simply understand that. I don't need to show it. On the reactant, I have SO3. Its coefficient 2, so raised to the power 2. So I write the equilibrium expression here. This is good. Now I have to plug those values that are given and solve for equilibrium constant. So let me go ahead and write that. So SO2, I have 0.44 molar. Okay, I will square that. And then O2, 0.22 as given by the question. I keep it as it is. Divide that by SO3 is 0.11 raised to the power 2. Okay, now bring your calculator and calculate this. 0.44 square times 0.22, divide that by 0.11 whole square. Let me get the calculator here. So 0.44 squaring of that gives you 0.1936 times 0.22 gives you 0.042592. Okay, divide that by 0.11 square. Okay, so that will give you 3.52. So let me write. Did I miss my pen? Okay, now let me write 3.52 is the value when I put these numbers in the calculator. Okay, and one thing that I forgot to mention is the equilibrium constant does not have a unit. Okay, so it does not have unit, no unit. Okay, so this is the final answer, because in advanced classes you will learn that equilibrium constant can be written as the ratio of activities, and when they are written as the ratio of activities, the numerator and denominator will have the same unit and they will cancel each other. That's why the K, the equilibrium constant, we do not write any unit. Okay, we simply write the number, the quantity. Now you can guess yourself, if K is 3.52, what does it mean? Right? It is greater than 1, right? What does it mean? It is slightly greater than 1. It is not like 1,000 times greater, just slightly greater than 1. What is the significance of that? Greater than 1 means the equilibrium lies to the right, right? And the products are the favored one. You can have that analysis on this. Okay. So in today's class, we learned about the equilibrium, right? We learned about how to write the equilibrium expression. We learned about what does the magnitude of K tell us, right? What is the information we can get from it? And then we finally here tried a numerical problem where the concentration of reactants and products were provided. We just plug them into the correct equilibrium expression and solve for it. All right? Please practice this question yourself one more time and check your answer. We will continue in our next lecture video. Thank you.